that's this one. In air, you only need this triangle that's to the right of the airline. Right? See the difference between this diagram and the methane one we were looking at earlier? It covers a large portion of that flammability diagram, right? So this is methanol. It's something to keep in mind. It's actually a highly flammable chemical. Okay, so now the question in our problem here was, if you have methanol, right, that's, in our case, we had it inerted in air, but let's look at it if it's vented to air. So say you have a methanol bottle in your lab, and you open it. Are the fumes flammable? In other words, do you want to keep it away from your hot plate or your Bunsen burner that's in your lab? The answer is yes, but let's just make sure. Okay, so how do we do this? What did the problem state? Problem statement, I have to go all the way back. Oh, there we go. 25 degrees C, 1 atmosphere. So we need to calculate the vapor pressure. Okay, for methanol, we go to Appendix E. It's 18.5875. You know how to do this. 3625 over, it's 298, 15 Kelvin, 34.29. That gives us the saturation pressure of 126.88 millimeter mercury. And you know what, I didn't calculate that, and I didn't calculate it in terms of if this one is vented to air, because in this particular case, it was inerted with 2 inches of water, and that is equal to, if we convert it, it is 2 times 760 over 406.8, and it is 3.736 millimeter mercury. Okay, so our concentration of methanol, or our fraction of methanol, is 126.88 over 760 plus our 736, which is equal to 0.166, or for our purposes, about 17% methanol. Okay, so wait. So if we just take 126 over 760, I mean, it's a little bit larger than that, but not by much. So the bottom line is, if you are venting this, if you're not inerting it, and you're just opening your bottle, right, our flammability limits are 7.3 to 36%. So that bottle of methanol that you have is flammable, right? Now, if it's inerted, then obviously it's not flammable in the bottle, right? But so let's put 17%. Let's put this number on that graph. 17% methanol inerted with nitrogen. Let's put that on your diagram. Okay, so inerted with nitrogen, that means in this case we don't have any oxygen, right? So it would be on the 0 oxygen line. Okay, so the question now, will this here be flammable if you vent this one to the atmosphere? So vapor escapes from this container, this inerted container over here, will it be flammable? So how do we determine that on the graph?
Go down.
We draw a straight line from this point down to 100% air. And if we do that, you will see, yes, it does cut the corner of that, right? It's inside of that corner. So the answer is yes. Even if you inert it and the vapor escapes, they will become flammable. Right. So then, how do we determine what is a safe methanol concentration? Okay, so we can do that on this graph because we need to avoid this region here, this triangle.
Go a little bit below, like 15%.
The nose of the flammability zone, right? So we can draw a straight line
You take
from,
this point
this
down to
mouse
here.
is terrible.
Draw a
From
line.
the 100% air through this crosshair. Oops. And then we
Dude, it
can
has to follow the
read
lines though.
what is now called the OSF,
What do you mean?
out of service
Like-
fuel concentration,
I just asked you.
OSFC.
Yeah, it goes down, but it has to
And as you
follow
can see, it's about
those lines.
14% methanol. So to do this safely,
So it will be like right
right, we would take that methanol container and basically drain the liquid methanol first. If we need to make sure that we take this vessel out of service, for example, to go in and weld on it. We drain the methanol, and then we reduce the methanol concentration of the vapor from our 16, 17% down to 14. Once we've done that, we can let air into that system. Because now you're outside of that flammability zone that we need to avoid. So this taking the vessel out of service is actually in part of chapter 7. Yes.
What's the point of the stoichiometric line?
What is the point of the stoichiometric line? So on that line, you have a stoichiometric concentration of oxygen and methanol, and you just add nitrogen basically. But it's to define this corner of your flammability diagram.
Okay, so doesn't that already cross where the 10%?
So you can, I like to see that we double check, right, these two lines and how far they are from each other, right? So that you take the line where the LOL, LFL line or the stoichiometric line crosses the LOC line.
Okay.
You should be fine, right, with just the LOL, LFL crossing the LOC, because right?
You should be fine the other way too, then, right? If you just use a stoichiometric line.
Yes, I believe so. I think that just expands though, most often. But you know, if we look at this, we can go back and look at where we have all the acronyms or abbreviations. What you can see, right, is that as long as you're below the LFL concentration, right, as long as you have a methanol concentration below 7.3, or
It just keeps going.
an oxygen concentration below 10%, you do not have a flammable mixture. You cannot ignite that. So that's the way to be safe at all times. Now, to reduce the methanol concentration, for example, below LFL, is going to cost you a lot more than if we just reduce it to 14% fuel concentration, right? And that's what's going. So in other words, you can be safe by reducing it to 7.3% methanol, but your boss is going to get mad at you because you used too much nitrogen and getting it that low when you didn't really need to. So, right, because what your company is going to do, they're going to pay for that pure nitrogen that you are using to avoid the flammability zone. So you want to make sure that you're cost efficient as well, and how you would do it. So basically, we were up here, in this case, right, we are really not, we don't have to reduce it that much. We were at 16, 17, so we just have to reduce it a few percent. But say, in the case of methane, when you have a pure gas, right, up here, then you have to go along this line, you add pure nitrogen, or impure nitrogen, we're gonna look at that too, down, and to reduce the concentration down until, I can't remember what I don't think we determined the out of service fuel concentration for methane, but you do the same. We had a much lower LFL in that case, right? So, but basically you have to go down here, reduce the fuel concentration until you reach the out of surface fuel concentration for your component. And sometimes there is a table in the book, it's in chapter 7, that will give you some experimental values. But I want you to be familiar and comfortable with doing it from the flammability diagram. Any questions on this particular problem? So this was so we've done it for methane. I think the homework has butane. Is it butane? There's an or acetone. I can't remember. Okay. I believe I had listed on the homework to look over problems that we had worked in class, and I had listed 6.6 and 6.7. But they're not gonna be included in this week's homework. They'll be included, so they'll be suggested problems for the exam instead. We're gonna focus on flammability diagrams, determining if mixtures are flammable, so we're gonna work a few. And now, of course, I can't remember which ones I said I was gonna do in class. So the key here, right, in determining, we've already done this, so I'm not gonna go over this in great detail. We did this, so for, let me see, methanol, of course, is not on here. But basically you would do the same thing, right? You need to know what the vapor pressure is, right? What's the vapor pressure? And these are all, if they are, right, storage vessels, 25 degrees C, you need a temperature and the pressure, right, to determine the saturation pressure of your component at those conditions. And then you need to go look up what is LFL and UFL. What are the upper and lower flammability limits in air for these components? And so if we do, let me see. Like I said, I can't remember which ones I said, but you have all of them. Let's do A, so this is acetone. It's a useful exercise actually, because, right, sometimes, more volatile components might actually be outside of the flammability limits, while less volatile ones have vapors that are immediately flammable. Okay, so for acetone, it's 16, 6, 5, 1, 3, 29, 40, 46, 298, 15, minus 35, 93, and we get saturation pressure of 22989. That's millimeter mercury. So Rx acetone is equal to 22989 over 760, and that is 0.3025, or 30%. Okay, so that's a decently volatile component, right? So if we go back and we look at LFL and UFL, it's 3% and 13%. Okay, so that means that not flammable. But again, that's not where you want to be, right? Because it's gonna, acid dilutes, it's gonna become flammable.
Isn't that kind of misleading?
It is misleading, yeah. So the answer to the question is it flammable? No, it's not. But let's put it on here, it will become flammable. And I think this is, right, so here's the problem too, right, that some operators might think that, okay, we have an inerted tank. It's inerted, so it's not flammable. But that doesn't mean that when things leak out, that it's not gonna become flammable, right? Okay, so we can do this for so if we look at benzene, that's also another highly volatile one, which is not flammable immediately out of the box.
What
Yes.
was an upper flammability limit on her percentage?
13%.
Oh, okay.
Sorry. There's supposed to be a period. So it's 3% and 13.
30%.
A little bit of a difference. Okay, so if you look at benzene, it's also a highly volatile component. It is not flammable. Straight out of the, I'm not gonna put numbers on there. You can practice on that if you want. Okay, so let's look at ethanol. Yeah, let's look at ethanol. So if we do the same thing, we calculate the saturation pressure using appendix D. Pressure is 59,136 millimeter mercury. That gives us concentration of 0.0778. Okay, or 7.8%. LFL and UFL. Okay, 4.3% and 19%. Okay. In other words, the ethanol coming out of your bottle is flammable immediately. So the other, right, all the other series is to repeat the same thing. You know how to get the saturation pressure, how to calculate that. The only difference what you might have to do is if you have, so you'll see why these are often inerted, right? If you have a tank of these liquids, they're often inerted so that you avoid this. So, and if they are, when you calculate the concentration in there, you just have to add the gauge pressure, right, to get the actual concentration, which is what you would put on the diagram. So what we're gonna look at, either I'll do it on Thursday after the quiz, is to how does things change if you're inerting